So it may seem a little peculiar, but there is some mathematics and even some kind of application of it. So what I will talk about is somehow work in progress, really work in progress, and it's kind of my concept that I came up about a year ago, and it started with a question if we can use a finite automata synchronization to design an asymmetric crypto system. So why it is finite automata synchronization? It's very simple answer, because I'm doing that at my PhD, so it's like natural for me. So first I will introduce the notions of automata and synchronization of it, and then I will go to the main part of the talk. So and I'm afraid that I can be disappointed, but everything will be fine up here. Okay, so the automaton is a triple of three elements, and the first is a finite set of states, and it's Q. The sigma is also a finite set of letters, the alphabet, and the delta is a transition function, and it may be partial one, and it goes from the Cartesian product of Q and sigma, Q times sigma into the Q. And just to make things clear, if delta is a total function, then we refer to such automaton as a deterministic finite automaton, otherwise as a partial finite automaton. Actually, the partial finite automaton also is a deterministic one, but we need some kind of differentiation between them because it's important in that talk. Okay, so now more notation. So we define also a sigma star as a set of all possible words over the sigma. So, and epsilon is the empty word. And also we extend the definition of delta for that sigma star in a very natural way. So we are just going from the state by the transitions. You can see the example here. If we just took the word AB and started and then applied it to 0, it would be 1 and 2, so the result would be 2. Okay, and the last thing from the notation side is we write Q.W or even A.W for the image of the set of states by the word, and it's also the classic image of the set of states by some function. Okay, and now what actually the synchronization is, and I think it's very simple concept, because the formal definition is that we say that the DFA is synchronizing if there exists a word W and the state Q prime, such that any other state is transisted to that Q prime by a word W. And or in other words, we can also say that the image of the set of states by that word is equal to some singleton. And we have also a nice algorithmic characterization of synchronizing DFAs. So we say that DFA is, so the theorem is due to Czerny, the most important thing, the most important person in the theory of synchronization of DFAs, I think, initiated it. I think it's one of the the one, no, it doesn't matter. And so the theorem says that DFA is synchronizing only if for any pair of states there exists a word such that it collapses them into one state. And that theorem actually gives us a pretty nice and pretty simple proof that the question whether the DFA is synchronizing is in a P class. So there is a polynomial time algorithm that decides whether a given PFA is synchronizing or not. What is what is important from the computational point of view. And the example is actually, it's easy to check that if we took the, if we would took that also. If we would took that word AB cubed squared A and applied it to any state, we will always end up in the state 1. Okay, so now it is actually the conjecture that you are seeing right now on the slide is one of the most important or the most important open problem in the theory of formal languages and automata theory, and also one of the most renowned in the computer science, at least the theoretical computer science, and it's also like the most of such pretty conjectures. It's very simple to state that if we have a synchronizing DFA, then it must have a synchronizing word of length that not exceeds the n-1 squared, where the n is a number of states of that automata. And that conjecture is still open for almost 60 years. There are proofs for various classes of automata, but the best known upper bound is cubic in general case, and actually is implied by the Cherny conjecture. Of course, there are some improvements, but it's still cubic. Okay, now the careful synchronization, and that is actually the notion that is the most important in my talk, and it is applied to a PFA. So it's actually the same as a synchronization. It's kind of generalization of notion of synchronization for a PFA, but so the definition is actually quite similar, but we have that restriction that for every prefix W prime of W, we have that for any state Q, delta Q, W prime is defined. And that is actually kind of restriction, because there is a theorem which was proven about 10 years ago by Pavel Matviunin, who have proven that deciding whether a PFA is carefully synchronizing is p-space complete, even in the case of binary alphabet. And just for the record, p-space completeness is believed to be even harder, even harder problems that NP completeness. It is believed, we don't know. So the other important thing about careful synchronization is that in that case we have there are some examples of some families that have shortest carefully synchronizing words of the exponential length in the terms of the set of states. And I think that is all about the introduction, and now why I actually took care of it, and because I just thought that it is interesting. So just some recap, that asymmetric cryptography is some kind of cryptography that uses two related keys, and public is for encryption and private for decryption. And of course, public key is widely distributed, while the private key must be kept in secret. And the third point is actually the most important for me, because as while I was studying, the most popular asymmetric crypto system that we were learning of was based on the number theory problems. For example, RSA, El-Gamal, and all other stuff. Even there were some improvements. For example, there were exchange of the field for the elliptic course curves, but the most popular, I think, that are based on a number theory problems. And of course, there are some examples of crypto systems, of asymmetric crypto systems that are not based on number theory. But I think it was some kind of intellectual challenge for me to come up with something. And okay, so now let's what I want to say right now. The first thing is I want to give some overview of the encryption and decryption algorithm, the main idea of it. And the second, I will say something about the keys. What should be the key? What should be the key? What cannot be the key? And how to deal with that problem? Because actually that is the problem that is the most important for me right now. So let's assume that we have a plain text P, which is just some word over the alphabet, binary alphabet 0 and 1, and we have MPFAs A1 to AM. And that is very important condition here, such that there exists W prime W, which carefully synchronizes every one of that MPFAs. And we are using that MPFAs to encrypt and that W to decrypt. So the encryption procedure is as follows, and actually I have the example because the slide is actually unreadable. So the first thing is create a directed graph G from the plain text, and that in the manner that if we have the plain text of k letters, then we take k plus 1 vertices and label consecutive edges of that directed path with the consecutive letters of the word, and that is here we have the example. Oh, and sorry, I forgot. In the example, we assume that the P is 0, 1, 0, and A1 and A2 are here. It's easy to check that there are some lacking P transitions here and here, and both of these automata are carefully synchronized by the word ABA. So let's look at the step first. The step first is actually simple. So the next step is each vertex VI in G replaced with a randomly chosen automaton P BI from that set of M automata. So in the example, it would look like here. So we replace the V1 with A1, V2 also with A1, V3 with A2, and V4 with A2. But it's actually whatever we want. It doesn't matter which of them is which. But the green, the red automaton is V1, represents the V1. The yellow automaton represents V2. The green automaton represents V3, and the blue automaton represents V4. So now let's go to the step 3. The step 3 is also for any two automata that are kind of neighbors, so they represent the neighboring vertices. Choose one of the states from each and add a transition that corresponds to the corresponding transition of the graph G, and that is here. So we are like it is written here. We are adding proper 0, 1 and 0, 1 edges. So if the green automaton is V1, then and that is V2, then we are choosing one of the states of that, one of the states of that, and joining them with the proper edge. And the same thing is between yellow and green and blue. So I think that is also kind of simple. The first thing, the fourth step, sorry, is to for all the automata that are in the ciphertext, choose k pair of states P and Q, and add a transition randomly chosen between them. So how it would look like on the example, and it looks like so for that red automata. So here in that example, the k is equal to 1, and the red automaton is we've added that orange 0. Here we've added orange 1, and everywhere we've added something between the states of the same automaton. So it's like some kind of obfuscating 0 and 1 edges. And actually, that is the last step is actually to kind of make that construction determine in the from the perspective of the set sigma. So what does it mean actually? So let's observe that every of that automaton is actually the partial automaton. So we just add some D transitions between that automata to make that construction a DFA from when we restrict that construction to the letters A and B in that case. And actually, what we obtain here is a ciphertext. So now let's go to the encryption, and decryption is actually, I think, really simple because then we know that every of that automata is actually synchronized, carefully synchronized, but by the same word. So we can apply to that construction the word W, and we will end up with 4 vertices, exactly 4 vertices. One of them will be from the red automaton, one from green, one from yellow, and one from blue. And that is the first theorem actually. And the second theorem means just that if we have that information of the vertex of the state and of the word, then we can recollect recollect which edge belongs to which automaton, and that results with which state is in the automaton that represents the same vertex and the same vertex of the input plain text. So having that, we can easily, so having some kind of partition of that construction for that automata which represents the vertices, we can easily recollect which of that edges of that 0, 1 edges belong to the plain text, and which of them aren't, and what's more, we can recollect from that construction from the partition the whole plain text, so we know which edge should be in which place. And actually, that is the whole decryption procedure. And now, what about the keys? The first most natural idea would be just to generate the MPFAs such that there exists a W that carefully synthesizes them all, and then we take that set of automata as a public key and W as a private key. But that is problematic. The first, because if we know the automata from which we build our ciphertext from, then we can easily determine which states are in which belong to which automaton from the public key. So that actually is the same what we are doing using that carefully synchronizing word. And the second is actually less important right now, since we know that it may be hard to come up with some generation procedure. So, but that doesn't mean that everything is lost, because recently I managed to prove that that deciding whether some proper subclass of PFAs is carefully synchronizing is NP hard, and the reduction that I used was simple, maybe not so simple, I don't know, but was a classic reduction from a pre-sub problem. So from that reduction and from that NP hardness, we can deduce a theorem which actually kind of gives us a hand, because we just know that there exists an algorithm that for a given pre-CNN clause phi in a polynomial time constructs an automaton A phi, which is carefully synchronizing, if and only if phi has a truth evaluation. And moreover, what is also true from my reduction is that moreover, E is a truth evaluation of that for that clause phi. Then there exists an algorithm constructing WI, which carefully synchronizes A phi. And having that, there is some simple observation. So we have something that from the given pre-CNF clause and some truth evaluation gives us some kind of partial finite automaton, which is carefully synchronizing by a word that corresponds to that truth evaluation. So now it is a very simple observation that if we have some formula phi and with n clauses and n variables, then if we restrict that, if we just take some sub-formula, so some formula that has only some subset of the clause of those clauses, that then E also works for that subclause, for that sub-formula. Possibly restricted to some subset of variables, but that is not important because that reduction can be easily modified to work in that case. So now the idea would be like that. The public key would be the clause phi, and the private key would be the truth evaluation key. I'm not an expert in that logical clauses, but I suppose that generating clauses and truth evaluation may be far easier than generating automata. So the encryption would be first generate sub-formulas. Here should be sub-formulas phi 1 to phi k, and use them to construct automata a phi 1 to a phi k. Then encrypt the message as stated before, and the decryption actually would be the same as stated before. Just use that word WE that works for all the clauses. So that is all that I have right now. I started some research questions because, of course, the most important for me right now are those automata constructed from clauses secure. So, if there is any possibility to deduce from that automata, from that construction, the sub-formulas used, because if that is true, then I must look for some other option and maybe modify that reduction, make some other construction, and actually that is my main research question. So thank you for your attention.